Welcome back to Bio 6612. In lectures for week 11, we're talking about random effects models, and in this lecture in particular, we're going to talk about random intercept and random slope models and how to implement them in R, as well as interpret fixed and random effects. We're not going to cover in this particular lecture is inference, like p-values and confidence intervals for those models. It's not as straightforward for this type of model as it is for cross-sectional data models, and so we're going to cover that separately in the next lecture. There's a couple extra readings here. These two textbooks are both open source textbooks that have to do with longitudinal data analysis and other modeling. And I think that they have some really nice examples. So I encourage you to take a look at them. So I'm going to focus on the pig weights data for most of the models I run here. As a refresher, that's data with 48 piglets that were weighed each week for 9 weeks to measure their growth in weight over time. And we've got data on the ID number, which is the identifier for each pig. The week number, which is the time variable goes from 1 to 9, and weight, which is the outcome, the body weight in kilograms of pig I at time t. I'm going to run a linear regression model, a random intercept model, and a random slope model with this data. So first, what I want you to do is load the semi-par library, which allows you to load the pig weights data. So first, I ran an ordinary least squares model, looking at the relationship between the outcome, which is weight, and time, which is number of weeks. And this, by running the ordinary least squares model, I'm ignoring correlation within the pigs, but you can still get estimates for your beta, which is the relationship between weight and time, as well as the intercept, which would be the weight at time when time is equal to 0. So now I'll get into my random effects model, first starting with a random intercept model. So the most popular R library for mixed models is LME4. And this is a continuously developed library with all of the sort of cutting edge stuff that has to do with mixed modeling. NLME is also another library. This is an older one. It doesn't have as much stuff in it as LME4, though the way that things are estimated is more in line with how things are estimated in like SAS mixed modeling, like proc mixed. And I'm happy to answer questions about that if anybody's curious. But for the models that I run, I'm going to, and at least mixed effects models, I'm going to focus on LME4. And another good reason for that is LME4 is better for GLMMs, which are the generalized version of linear mixed models, which we're going to talk about in the last week of class. So when you run a mixed model, a linear mixed model using this package, or any other package, you get estimates for both their fixed and your random effects. And one thing that's interesting is if you don't specify extra correlation structures, then the fixed effects actually have the same value as the OLS model. Well, which means that you're going to have the same interpretation of the population mean as you would in the mixed effects model as you would using least squares like we just did. However, what's different is the standard errors. So you would get different inference, different confidence intervals using this type of modeling. And another thing to note is when you use LME4, it does not provide p-values for your effects. And there's a couple of reasons for this. However, you can still do inference. But I'm going to talk about that in the next lecture. But the overall reason that LME4 doesn't provide p-values for the models is that they want you to. There are some situations in some types of random effects models where the standardly calculated p-values don't really make sense, so they don't want to have people misuse or interpret those, so they just don't provide them. But we'll talk about that next lecture. So this code chunk here is for running that random intercept model on the pigs data. So first I'm loading the LME4 library. The main function we're working with is this LMER function. Then you have your formula statement here, your formula. And this is similar to formulas in other functions we've worked with. The outcome here is weight. The fixed effects are going to be stated the same way by just listing the name of the variable. And then this notation that I'm bracketing is the notation that you use for adding random effects. So that's what's different. And in this case, I'm only adding a random intercept on ID number. So this notation on the right-hand side of this line, we put ID number, that's the time variable. The variable that you put there is whatever variable is sort of being repeated, is indicating what the unit is that you're doing the repeated measures on. And then on the left-hand side are the variables that you want to have random effects on. So in this case, I just have a 1 because I only want to have a random intercept. Random intercept, so it would be random intercept on the ID number. So a random intercept for each pig is what that's setting up for us. And then the data statement just says that we're using the pig weights data. So I'm using a summary then to look at the outcome of that model that I've just read, and that's on the next page. And so you can see the summary here. What's returned looks a lot like what you see from LM or GLM, but there's a couple differences. It provides the formula for you up here. It gives you some criterion for convergence, and the REML is how it was estimated. That stands for restricted maximum likelihood. That's just the estimation procedure. I'm not going to talk about that more in this lecture, but I will touch on it briefly next lecture. Then it gives you a set of random effects, your random effects, and your fixed effects. So the fixed effects are going to be similar to what you would normally see where you have your estimate. In this case, we have an estimate for your intercept, that's beta 0. And your estimate for your number of weeks, that's beta 1. And it provides standard errors and t-value as well, though this is what I'm saying, that they're not giving you p-values for your fixed effects. What's new is you also have random effects. And it doesn't provide you so you're going to have a separate random intercept for every pig in the data set. It's not going to list those out in the summary here, though you can extract those from the model that we just ran. But what it will give you is, okay, for this particular random effect, in this case the intercept on pig, which is that first row, it will give you the variance of that random effect. It will also give you the residual variance, the measurement error. And I'll talk about that more in a few slides. So it can be helpful to visualize the fitted values for these models just to understand what the fits actually look like and how well they're capturing the variability in your data. So what I'm making here with this fancy ggplot is a spaghetti plot with the fits from that model overlaid. In this case, every pig has the same estimated slope on time, but different intercepts. So we have it because this is a random intercept model. And I don't know if you remember from last lecture, but if you have a population mean here, say that's the population mean green time. So you have time and maybe weight as your covariate. When you have a random, hold on. Let's try that again. I want to get a different color. Okay, and then so maybe that purple is the population mean. Each pig is going to have their own intercept, means they're going to have the same sort of weight trajectory, but it can be a different intercept. So that means it's just going to hit the y-axis at a different place. Okay, so plotting that here. So what I did is the first thing I did is I took that pig weights data and I added a new variable called fitted values, which is the y hat values, sort of the estimated y's from the model, that I can extract from that random intercept model using the statement fitted, and that just gets the fitted values. And you can use that for LM as well, so you might be familiar with that function. So the model that we fit was y equals beta 0 plus beta 1 times time plus beta, that will actually be your random intercept. So for each pig is represented by I, so your fitted value y I hat is going to be the sum of the population intercept plus the subject specific population intercept, which is this beta 0, plus your subject specific intercept, which is your beta 0 I, plus time times your beta 1. That's where that's coming from. So I extract those fitted values. In this case, I'm just going to plot 4 pigs just to make visualization easier. That's what that filter line is doing. I'm just extracting 4 of the IDs. So I'm only looking at 4 of the pigs. And then I'm making a ggplot where I have the observed values as a point in the line, a spaghetti plot of the observed values. Then I'm also putting a population mean on there in red and each of the subject specific means that are calculated in blue. So here's what that plot looks like. So in the black lines show each of the pigs' original data trajectories. The blue lines show the fits, the y hat I fits for each of the different pigs, and the red is the population mean, which also is coming from that model. And you can see that the blue line for each of the pigs has a line that's parallel to the population mean, but it's just shifted based on that own pig's particular intercept. So the red line up to this blue line here would be one of those beta I intercept values. And you can see that the fits seem pretty reasonable here. However, let's say for this pig up here, the random intercept tends to be higher than the pig's values at the beginning of time in earlier weeks, and then lower than the pig's actual weight values in higher weeks. So it's not a perfect fit. So now I'm going to jump into some interpretations for this model. So we can interpret the beta coefficients of the population effects the same way we would in normal linear regression. So for beta 0, for this model, we had y equals beta 0 plus beta 1 times time plus beta plus a random intercept plus an error term. And the beta 0 is the intercept term, which in this case we would interpret as the weight in kilograms at time 0. So, and we'd say here on average the pigs weigh 19.4 kilograms at birth. And the beta 1 is just the slope for weight over time. And in this case, we would say on average pigs grow 6.2 kilograms per week. That's that from that beta 1 value. So random effects models are extra useful because they can partition the variance into the between variance, between subject variance, and within subject variance. So it's good to look at the variance components as well. The output of the random effects output gives those variances. The first row is the variance of the random intercept, which can be interpreted as the estimated variance in between pig deviations, or the between subject variance. And then the second row gives the residual variance, that's the measurement error variance, or the within subject variance. And we can see in this case the variance between pigs is higher than the variance within pigs. And then we can use this information to calculate the interclass correlation coefficient, or ICC. The ICC is calculated here, and that's the correlation within observations on the same subject, which is given by the between subject variance divided by the total variance. And in this case, it's 0.775. This number is always going to be between 0 and 1. And when it's higher, when it's closer to 1, that means that there's more of the variability attributed to differences among subjects. In this case, you would interpret that as that 77.5% of the variability in pig weight is attributable to differences among pigs relative to natural variation within pigs. So large ICC indicates observations within a pig are strongly correlated. However, as ICC approaches 0, responses are independent, even within the same subject. So accounting for within subject correlation is not as necessary when you have a really small ICC. So when sigma squared is much bigger than sigma squared b, we might not really need that random effect. So next I'm going to look at a random slope model. The code below runs the random slope model for the pig weights data. And this model is quite similar to what I ran before. You're still using the LMER function. You still have weight as the outcome. You have the same fixed effect here, which in this case is num.weeks, which is the time variable. And what's different is the random effects specification, which is given here. So on the right-hand side, we had the time variable, or whatever you want to have a random effect on. This is your Z matrix. And back in that terminology that you used from 1 or 2 lectures ago. And then on the left-hand side, you have the actual random effects, the B term. So in this case, we have 1 still, because we still want a random intercept. That's B0I. And then num.weeks is a random slope. That's B1I, because we're going to put a random slope on the time variable as well as the random effect that we had last time. So we can look at that model. It's printing out here. And I'll just zoom in a little bit so you can see it a little bit better. So a lot of the things that we have are the same as before. The fixed effects are going to be the same, and these are actually the same values that we had before for the fixed effects. The standard errors will be different though, because adding the random slope means that you're going to have a different variance calculation for the overall variance in the population, which means different standard errors. And the random effects are different as well, because now we still have a residual variance. That's your sigma squared value. But now we have 2 other variants as well. First is the variance of your random intercept. That's what we called sigma squared b last time, but I'm going to call it sigma squared b0 to indicate that it's the variance for the random intercept. And then we have a second row, which is the variance for the random slope. So I'm going to call that sigma squared b1, the variance for the random slope. And you can see that the random intercept has much higher variance at 6.986 than the variance for the random slope, which only has 0.380. That really indicates to me that the intercept is probably absorbing more variance than the slope and is probably a more important component of this model, but we can look at that visually in the next couple of slides. And then the last thing to mention here is we also have this correlation of negative 0.06, and that's the correlation between the fixed effect and the two random effects. I'm sorry. So again, we make an assumption that the errors and the random effects are independent. So that means that each error term is independent of the random slope, and each error term is independent of the random intercept. However, we do not assume that the random slope and the random intercept are independent. So that means that we have some correlation between those two, which is calculated in the model here. However, in this particular case, the correlation is not large. Again, I find it really valuable to plot random slope models in the same way that we plotted the random intercept model, just to evaluate how well the model is fitting our data, visually at least. So I'm going to do the same thing here, where I extract the fitted values from the model, the y-hat values, and I put them into the data frame containing the original data. And then I'm filtering out just to look at 4 subjects to make visualization a bit easier in this case, but I'm doing that for teaching purposes. Normally I would look at the entire data set. And then I'm plotting the observed data as a spaghetti plot plus the population mean and the actual fits from this model. And that is all plotted here. So from the last model, the random intercept model, we had strictly parallel lines against the mean. But in this case, now each subject, or each pig in this case, has their own slope as well as their own intercept. So you have the population mean in red here, and each pig has a slope that varies and an intercept that varies around this population mean. So for example, for this pig here, they would have a higher slope than the population mean. Sorry, a higher intercept because it's above, the start is above that red line, but they would also have a higher slope. It's sort of steeper, the slope is steeper for this pig than it is for the population. And that slope accounts for the fact that this pig not only starts out at a higher weight than the rest of the pigs in the data set, but also seems to be growing at a faster rate over time than the rest of the pigs. Again, we can interpret the fixed effects in this model much the same way as we would interpret the fixed effects in a regular or ordinary least squares model. And these are interpreted as population level effects. And because we haven't added any new fixed effects to the model, we have the same interpretations as last time with the random slope model. The only thing that's different is the standard errors are going to be different. So you would have different confidence intervals and different inference potentially, but you have the same interpretations of the actual mean. Where on average pigs weigh 19.4 kilograms at week 0, and on average they grow 6.2 kilograms per week. Now finally, I'm going to look at another example. In this example, which I'm calling the student GPA data set, we'll assess factors predicting college grade point average. And each of 200 students was assessed 6 times, so 6 different occasions each semester for the first 3 years. And so we have observations clustered within students over time, and we also have balanced data because everybody is measured at the same time points, and we don't have missing observations. So other variables in the data set include GPA, which is the outcome, occasion, that's the time variable, with 6 time points per person. You have sex, which is binary, indicating male or female. High GPA, which is the high school GPA of each student. And job, which is how many hours a student worked. And this is actually a 3-level categorical variable. This data set comes from one of the textbooks, the open source textbooks I referenced at the beginning of this lecture. And you can load it in directly from the internet using this line of code here. I'm going to call that data set the GPA data set. And I always like to do exploratory data analysis of the data set before I do any kind of modeling. But I think it's especially important with longitudinal data to get a good sense of what your data actually looks like. So the first thing I'm doing here is I'm going to make a spaghetti plot of that GPA data where I look at the GPA at each of the different 6 time points. So these first 2 lines run that spaghetti plot. And then I'm adding a separate line on top of it where I'm just putting, you can only kind of see it's a little bit not dark, but there's a green and a blue line, and that's just overlaying 2 of the students that I randomly selected, just so you can get a sense of those 2 students' trends, because it can be a little hard to see in this data because it's a bit messy. So on average, though, it does seem to be, this looks like students' GPAs are increasing throughout the course of over time, so with each semester. And those trends seem to be variable within people. So you can see that this blue subject starts out with a GPA around 2.8, goes a little bit lower in the second semester, and then increases a lot by the end of the time that they're in college. And this red subject here also starts out with a low GPA, increases a little bit, dips back down, and then increases a little bit more, but never has that dramatic increase that the blue subject has. So I want, let's say I want a random, I think that we should have a different intercept for each subject. So you can see that where people start does vary pretty greatly, and it does seem to, and that people end up in different spots as well. So it seems like having a random intercept, at least in this model, probably to account for that variance is a good idea. So let's say I want a random intercept model that looks at the GPA over time and controls for sex and high school GPA. So what does that model look like? Well, in terms of actually writing out the model, I'm going to write out my fixed effects first. I have a population intercept plus a beta for time, which is called a, plus I want to have the sex as a variable as well. And that subject's high school GPA. Plus some error. So that's the actual model that, oh, and then I forgot the random effect. So plus the random effect, which in this case is going to just be BI, because we want just a subject specific intercept, plus the measurement error. So in this case, what are the fixed effects and what are the random effects? Well, the fixed effects are going to be here. Those are the population level effects. And then our random effect is just that random intercept. And I'm modeling it the same way I did for the random intercept model for the pigs data, where the outcome is GPA, The fixed effects are written out here the same way you would write a fixed effect in an LM or a GLM model. And this term contains the random effect where the ID for the person is on the right-hand side. Whatever is being taken multiple measurements of on the left-hand side specifies the effect. So one, just a 1 on that left-hand side there specifies that I want a random intercept. So looking at that model itself, I just have the random and the fixed effects printed here. You see your estimates for your fixed effects written out, and estimates for random effects as well. So we have a residual variance. Our sigma squared is roughly equal to our sigma squared beta. And so let's plot some of those results. So again, I'm going to plot this in much the same way I did last time, where I only grab some of the subjects to make visualization easier, and I make a spaghetti plot, and then on top of that I overlay the fits from that random intercept model and as well as the population mean. That plot is given here. So each of the random intercepts is parallel to the population mean, which it does seem that the GPA is increasing on average over time. And some students have a higher starting point and they tend to finish with a higher starting point and vice versa. However, it does seem that for some students at least, they don't necessarily follow along with their intercept. It means that it seems that some people, that maybe this intercept is not capturing all of the variability that we see. And so what's another way to look at that? Do we think that the random intercept is adequately capturing the within subject correlation? And one way to look at that is if the residual is randomly distributed around 0 and heteroscedastic. So let's look at those residuals. And you can see here that, yeah, they're randomly distributed around 0 at each time point, but it seems that at certain time points, especially the time points earlier on, the variability is around 0 is larger than it is at some of the other time points. So that suggests to me that maybe we want to consider adding a random slope to this model as well. But we're going to talk a little bit more about evaluating models and also getting inference on both your fixed and random effects in the next lecture.